Hello, today I will evaluate this series using complex analysis. So I will need three things. The first thing is that the series converges. The second thing is that n choose k is equal to 1 over 2 pi I, the integral over the unit circle of 1 plus z to the n over z to the k plus 1 dz. And the third thing is the geometric series formula, which says that the sum from 0 to infinity of q to the k is equal to 1 over 1 minus q if the absolute value or the module of q is strictly less than 1. Okay, yeah, if it's strictly less than 1. That's all that I need. So in the previous video we proved this and this, and this is known, this is well known. Yeah, so to evaluate this series I will use these three facts and the residue theorem. So let's begin. So the integral from n equal to 0 to infinity of n choose k over 5 to the n is equal to the sum from n to infinity of 1 over 5 to the n. So I will replace this by the integral representation, which will give me this 1 plus z. Okay, this is not choose, this is 2n choose 2n choose n, so I will get this over z to the n plus 1 dz. Now I will exchange the order of integration and summation to get the integral over c of the sum from n to infinity of 1 plus z. So I will write this as 1 plus z to the 2 to the power of n over 5 to the n, and this z to the n plus 1 I will write it z to the n multiplied by z dz. This z I will make it go out like this. I will, because it doesn't depend on n, to get the sum 1 over 2 pi I, the integral from over c of 1 over z, the sum from 0 to infinity of, okay, 1 plus z over n of 5z to the n. Okay, no, squared all of this to the n, of course, dz. Now using the geometric formula, the geometric series, so you can prove that the module of this is less than 1. We will prove it in the, I think we proved this in the previous video, but if you want to check, you can check. So this will be the 1 over 2 pi I, the integral over c of 1 plus z, okay, 1 minus 1 plus z squared over z. Now if you multiply top and bottom by 5z like this, you will get that this is equal to 1 over 2 pi I, the integral over z, 1 over z. So this z will simplify with this one, and you will get 5z minus 1 plus 2z plus z squared, because I developed this. So finally, okay, so if you calculate how much is this, you will get minus 1 over 2 pi I, the integral over c, 5z squared minus 3z plus 1 dz. Now, to evaluate this integral, we will calculate what are the zeros of this polynomial. So to know what are the zeros, we need to use the quadratic formula. So if you calculate delta, you will get the minus 3 squared, which is 9, minus 4, which is 5. So we'll get z minus 3 plus square root of 5 over 2, and then multiplied by z minus 3 minus the square root of 5 over 2 dz. Now you can calculate these zeros and see that this is bigger than 1, but this is less than 1. So this 0 is not in the unit circle. So by the residue theorem, we'll get that this is 1 over 2 pi I multiplied by 2 pi I multiplied by the residue of this function, I will call it f, at the 3 minus square root of 5 over 2, like this. But because 3 minus square root of over 5 over 2 is a simple pole, the residue of this function at 3 minus square root of 5 over 2 will be just the limit as z goes to this 0 of z minus 3 minus the square root over square root of 5 over 2 multiplied by f of z, which will be just minus 5 3 minus the square root over 5 over 2 minus 3 minus the plus square root over 2 over 5, which will be exactly the square root of 5. There is no 0 here, so it will be minus the square root of 5, which is so this will be the sum from 0 to infinity of Cn choose to from C to n choose n over 5 to the n is exactly the square root of 5.